Hello everyone, welcome back. We'll do another example from this textbook. This time we'll be looking at the example from listing 7.5, which is a verification circuit for the UART design entity that is shown as a simplified block diagram over here. Essentially the application in this case involves the DE1-SoC board that will implement this circuit, the UART controller, which will talk via a USB to a UART controller to my computer, to my laptop here. Inside the FPGA, the UART will receive what we send via the UART communication protocol. Will add 1 to what's received and send it back, echo back that incremented data to the host PC, where I'll be using a terminal to for this application. Here is a somewhat more detailed block diagram of this testing circuit. So this is going to be my FPGA on my DE1-SoC, not DE1-115 board. The UART controller will talk to the host PC via the UART communication protocol. I'll be sending from the host PC some data which will be received inside the FPGA by this UART controller. We'll add 1 to it and then echo that back to the host PC. If you double click, if you zoom in into the UART controller, then this design entity UART controller becomes somewhat a little bit more complex, and I assume that you have already looked through the textbook and you've got an idea about what this design entity here does. Essentially it's a couple of other design entities, including FIFOs, buffers, on the receiver and the transmitter design entities, as well as the baud rate generator. So we will not go into the details of discussing that, but we'll look at how exactly this works in practice on the DE1-SoC board. So I assume that you have already read the textbook and you know what we are doing here. So that is essentially the general description of what this application does. Now for that we need a UART to USB or USB to UART controller, which I have already hooked up here between the board and my laptop. In the code which I made available on GitHub, you will see in the top level that VHD, which is this testing circuit. I have a couple of comments at the top which will show you what connections need to be made between this USB to UART controller and the general purpose IOs that I selected to use to connect to the UART controller inside the FPGA. And these are VCC and ground. The sixth one is the ones as you count from the bottom up here on that GPIO 0 connector, and the port I'll show you in a minute. But here on the bottom left one in that connector, I need to connect the TX of the USB to UART converter, and then the right one I need to connect the RX of the USB to UART converter, which will connect to the TX inside the FPGA UART controller. So I have already this project and Quartus to created, compiled and programmed the FPGA board. Let me show you the connections. So the connections are the VCC and ground. The first two coming here to the VCC and ground as I count from 1 to 6 connectors, and then as I showed you, the bottommost ones of this converter are connected as shown over here to the TX and RX of the USB to a UART controller. So the FPGA board is now programmed the USB to UART converter connected with the right connections, the 4 jumper wires that connect the USB converter to this 4 GPIOs, 1 VCC, ground, and RX and TX of the UART controller inside the FPGA. If you go into a little bit more details of this project, you will see that this horizontal segment of the first 7 segmented display is lighted up, telling me that the received buffer is empty. Key 0 is a reset signal, and then key 1 will be the control button that the user can control to echo back what's received inside the FPGA UART controller back to the host PC. The only thing that I need to show you here is the termite terminal, which needs to be connected to that communication, to the right communication port, and more importantly, have the baud rate set to 19,200, because that's what the UART controller inside the FPGA has hard-coded as a baud rate. So right now we are ready to send, for example, 1, 2, 3, 4, 3, 4 up to 9. So I'm sending all of this numbers from 1 to 9. As you can see on the FPGA board, the buffer is not anymore empty. I have a couple of LEDs that show also the binary representation of what's being right now on the head of the FIFO. But most importantly, to send back, and as you will see as I press key 0 over here, I'm sorry, key 1, the data that is in the received buffer will be incremented and sent back, echoed, or looped back to the host PC. So you will see then here in my terminal, as I press key 1, the data that I sent is incremented, sent back. So if I press key 1 once, you'll see here I received back 2. If I keep pressing key 1, you will see that I'm getting back 3, which is the second number that I sent, incremented, and so on, as you can see. Now I have sent back to the host PC from the FPGA the 8, which is incremented, and the next one would be 9 that is incremented. Remember, here we're talking about ASCII codes that are incremented. So if I send back 9, you'll see here